Section 22.9, Transformers. So perhaps the most important application of mutual inductance and self-inductance together is highlighted with transformers. There's more than meets the eye here, so you're going to want to see. A transformer is a device for increasing or decreasing an AC voltage. The way that it works is we have an AC generator that sends current through the primary coil. This primary coil has an iron core that connects it to a secondary coil. The iron core is easily magnetized, and so it causes the magnetic field lines to pass from one to the other very directly, so that there's very little losses. The secondary coil has another number of turns and can be wired to something else. But within the secondary coil, because of mutual inductance, when there's a current from the AC generator, there's an EMF in the secondary coil that's equal to negative times the number of turns, NS, times the change in magnetic flux over the change in time. But we also have an EMF induced in the primary coil because of self-inductance, and that's equal to negative the number of turns in the primary coil times the change in magnetic flux over the change in time. And because of the efficiency of these transformers, the change in magnetic flux over time is the same for the primary coil and the secondary coil. So these two terms are in fact equal to each other. Oops. There we go. So the delta phi over delta t. What we can do then is divide the EMF of the secondary divided by the EMF in the primary coils. And these two terms would cancel out, the negative signs would cancel out, and we're left with this equation, that the EMF in the secondary coil divided by the EMF in the primary coil is equal to the number of turns in the secondary divided by the number of turns in the primary. And if your transformer is well designed with very little resistance, then it turns out these EMFs are very close to the terminal voltage, what you would actually get if you connected something to it. So instead of writing this in terms of EMFs, oftentimes we switch to using voltages. And this is known as the transformer equation, that the voltage in the secondary relative to the voltage in the primary is equal to the number of turns in the secondary divided by the number of turns in the primary. This allows you to change the voltage in any instance. For instance, if you plug something into the wall with your, say, your cell phone charger, your cell phone charger is plugging into a 120 volt wall receptacle of the AC source. But your cell phone doesn't need 120 volts to charge, right? It needs like 3. So your charger actually has a transformer to adjust the voltage so that you're not giving too much voltage to your cell phone and overpowering it. And it just has to do with the number of turns in the two coils there. Pretty wild. Now, something that does stay the same in both the primary and the secondary is the power. The average power has to be the same. And that's because we aren't gaining or losing things. We aren't cheating energy here. So the power in the secondary on average needs to be equal to the power on average in the primary. If we remember, power is equal to current times voltage. So the current in the secondary times the voltage in the secondary is equal to the current in the primary times the voltage in the primary. If we then divide this out to get the currents on the same side and to get the voltages on the same side, right? I could divide this by Vs to cancel it over here, instead have it over here on the right. And I could do the same with dividing out my IP, which would cancel it on the right, and we'd be left with this equation here, right? That the current in the secondary divided by the current in the primary is equal to the voltage in the primary divided by the voltage in the secondary. And based on our transformer equation, the turns ratio would match the voltage, right? So voltage in the primary divided by voltage in the secondary is the number of turns in the primary divided by number of turns in the secondary. What does this mean? Well, the bolded statement highlights what this equation is telling you. You can have a transformer that steps up the voltage to a higher value, and it will simultaneously step down the current. You can also instead have a transformer that steps down the voltage, and by lowering the voltage, you will increase the current. This is really valuable because current is useful for powering things like charging your cell phone, but current is also where you can have a lot of loss if there is resistance, like if you need to transmit some electricity over great distances. So with this in mind, our electric grid uses transformers. How so? Well, we have a power plant, right, that is probably an AC generator in there, right, using the steam to power the turbine to generate electricity. Cool. But rather than keeping it at a low voltage with high current, which would be a huge amount of losses, we step that up to really high voltage, right, 240,000 volts. And we send it miles and miles on these high voltage transmission lines, wires that you don't want to touch a couple of wires there because that would be a lot of voltage that you could short out, right? You also don't want this at your house because this would be too much voltage for all of your electronics. So there's a substation once the electricity gets closer to your house that steps it down to a lower value. And then there's smaller power poles that can step it down even further to a more manageable 240 volts. And by stepping it down in voltage, it's stepping it up in current, which means you're able to power more of your devices. So transformers are all around us, and hopefully you've seen some of the amazing benefits of electromagnetic induction. This wraps up chapter 22.